So, we talked about digital devices earlier in this workshop, but what does the word digital actually mean? Is it as simple as saying anything is digital if it is based on numbers? Well, yes, but not quite. The term digital originated from the word digit, like our fingers, because we use these for counting. At least I do. In a computer or digital device, all text, all numbers, pictures, sounds, all of that are represented through a combination of numbers. And before we look at how computers or iPads, mobiles use numbers, let's think about how we humans count. Most commonly, humans deal with numbers in base 10. Or what you might say, counting in multiples of 10. Why in multiples of 10? You might have guessed it, because most of us have 10 fingers. If you are a T-Rex, then you would count in 6, because you would have 6 fingers. But yeah, most of us have 10, so let's start by looking at this table of multiples of 10, or what I will call my base 10 table. Let's begin by breaking down the number 123. Each column in this table represents a multiple of the number 10. For example, the middle column is 10 times 1 and the left column is 10 times 10. So in this example, the number 123 is comprised of 100 times 1 plus 10 times 2 plus 1 times 3 in the base 10 system. Hopefully this will sound super simple, but it is important to remind ourselves how base 10 works before we look at how computers represent numbers. Base 10 works well and is convenient for humans, at least after you have spent years and years learning that system, but it is not convenient for computers, and computers, like all digital devices, are electronic and they represent numbers using base 2. Base 2 is a binary system, which means that each digit that a computer stores in either as 1 or 0, like an on-off switch. And these binary digits are called bits. Since a single bit can only contain a 1 or a 0, they are typically put together into groups of 8 bits, which are known as bytes to represent larger values. You can remember that from the T-Rex, the bytes. Now let's take a look at how we represent 123 using base 2. In base 2, we count in multiples of 2 instead of multiples of 10. Looking at this chart, we see the first number position on the right counts in 1s, then 2s, then 4s, then 8s, and so on. You'll notice every bit to the left has 2 times the value of the previous bit. Here we see that the number 123 in base 2 is made up of 64 times 1, 32 times 1, 16 times 1, 8 times 1, 2 times 1, and 1 times 1. I know binary numbers may sound complex, but let's think about them in another way, by using a card game. If you take a look at these 4 special binary number cards, on the front there is a number and then the back is blank. In this example, all the numbers on the card are showing. What do you notice about every card? Each card to the left increases by a multiple of 2. What is the total number when you add all of the cards together? 15, isn't it? Now look at these cards. You can see that we flip 2 cards over. What is the total now? Yep, it's 9. When a binary card is showing a number, it is represented by the number 1. When the card is flipped over, it is represented by a 0. So the binary number in base 2, 1001, equals 9 in base 10. So let's take a look at this next set of 8 binary number cards, which is known as a byte. What is the binary number and base 10 value for this card? In this situation, the binary number is 01001, and the base 10 value is 73, isn't it? So how would you represent 14 in binary numbers? Could you do that? The answer would be 0000111. We would add 2 plus 4 plus 8. What if we turned all 8 cards over? what would it add up to then? You could pause the video if you need to. At this point, just count them all together. Hopefully you would worked out it would add up to be 255, which is the biggest number we can store in a byte. If we want a larger number, we would need more bytes. Computers often use up to 8 bytes together, which is 64 bytes to store numbers. Wow! Now you know where those numbers come from. So now that we have an understanding of how to represent numbers based on the binary system, we can look at how bytes can be used to represent text. Since computers use a standard conversion system called UTF-8 to represent characters. And here are some examples of how values represent characters on a computer. When we type a character on a computer keyboard, it is internally converted to the underlying binary value for storage and processing. As you can see that 01000001 in base 2 creates a capital A, and 01000010 creates a capital B on a computer. Now you can imagine how representing characters in this way makes it possible to type text and see it displayed on a screen even though the computer is storing binary numbers, not letters. Now let's take a look at how bytes can be used to form pictures on a screen. Pictures like this Mindlab logo, for example, are actually represented by bytes of data on your computer. But how does that work then? When looking closely at an image, you will see that it is made out of lots of little dots, which are known as picture elements, or pixels for short. The pixels in most screen images are represented by 3 bytes in the computer. There is 1 byte for each primary color of light, so there's red, there's green, and there's blue. As we stated earlier, each byte holds a value between 0 and 255, and this determines how much of a red and green and blue light should be included in the 1 pixel. By mixing these primary colors, we can create millions of different color combinations. When you put all of the pixels together, then you get your image. For example, if you zoom into the Mindlab logo, you can actually see the different colored pixels that combine together to make the full image. Now you should have an understanding of how computers represent data internally using binary numbers and how those binary numbers can be used to represent different types of data. You should tap yourself on the shoulder for at least 0.0000101 times. Hey there! So let's think like a computer program and try and predict how the program might behave based on logical thinking. It's the same type of logical thinking that we use all the time, at least I do. For example, if it is raining outside, most of us might logically think, I need my umbrella. Sounds logical. Once we know the basics of the programming environment in Scratch, we can use logical thinking to make decisions. For example, if we make the sprite move several hundred pixels in any direction from position x0, y0, then it will travel so far that it will disappear off the screen. When using logical thinking, we use our past experiences and what we learned from them to predict what will happen when a particular piece of code is run. To predict the behavior of a program, we simply start at the beginning of the code and work through each block at a time. We might start by making a note that this particular piece of code will run when the green flag is clicked, that the sprite is in the middle of the screen, and then the pen is down. If we added the following blocks -90 and 0, followed by -90 and 90, and the pen up, then we would expect the sprite to draw an L shape and finish at -90 and 90 with the pen up. Each time any of these values changes, we should make a note because it will make it easier to predict the behavior of the program at any point in time. This process of looking at each step of the program in turn is known as a walkthrough, and in program development we often perform walkthroughs with other people so that they can help us to understand if our code will behave as expected. Having a second pair of eyes to perform a code review is always a good idea. Another important aspect of understanding how code behaves is to recognize and celebrate those various of ways to write code to solve the same problem. For example, you may find that you have run out of milk and need to get some straight away. Perhaps there is a dairy around the corner where you can buy milk, or there's a supermarket which is a few kilometers away. The milk may be a bit more expensive at the dairy, but going to the supermarket may be more difficult and take longer. The final decision will probably come down to how much time you have and your budget. But yes, in programming we find the same types of situations. For example, one piece of a code may solve the same problem quicker, but another may be more accurate, even though it takes longer. And you might even solve something else at the same time. Choosing between different algorithms is often a case of deciding which advantages or disadvantages of each are most important to you. Now let's check out these two algorithms on Scratch. They both perform the same action, but which one do you think is better? The algorithm on the left explicitly lists every step, while the algorithm on the right simplifies the code by utilizing the repeat block. If you find that you are coding the same blocks over and over again, then it is often possible to replace these with a repeat block. The code on the left accomplishes the same goal, but using the repeat block will help reduce the risk of error and make the code easier to follow. Here is another example using Scratch. Let's assume that we would like to draw a circle on the screen. Here are two different algorithms to do just that. Just take a moment to see how they are different. Can you spot that? Hopefully you can see that the algorithm on the left draws a circle by moving the pen 1 pixel at a time and then turning by 1 degree, 360 times. In contrast, the algorithm on the right moves 20 pixels at a time, turns 20 degrees, and only needs to do this 18 times. And here is how the two algorithms behave when they are run. You can see that the first algorithm runs quite slowly, whereas the second runs much more quickly. But the drawing of the circle is a little less accurate. When you are writing your own code, there is no single right answer to solving a problem. There are many different ways of coding one solution. It is up to you to choose the one that you think best solves the problem. The one is the most suitable, efficient, and hopefully sustainable of them all.